Hello everyone, it's June the 4th. We're gonna do an early one today. My phone burned yesterday, and I don't know why. I was listening to podcasts and suddenly the phone didn't work, and then I touched it. It's super hot. I got scared. I thought it can explode or catch on fire. I was able to get the SD card out, but the SIM card is melted, and the plastic is melted, but I'm not sure if the SIM card is still working. And then I thought, I couldn't leave it on the counter. It's gonna catch on fire. I also cannot put in a dumpster because the dumpster might catch on fire. So the solution is I put in a bucket filled with water. So it's still underwater right now. That's very scary. Battery, I think something wrong with the battery. The phone's been, I mean, I've been having it for six years. So it's an old phone. Maybe the battery is faulty. Something short-circuited. It always happens when the device is too old. All right, so yeah, it's interesting. Interesting happened last night. All right, let's take a look. Who we have today? Open the lock. Yeah, open the lock. We need to ask the lock-picking lawyer for this. You have a lock in front of you with 4 circular wheels. Oh, he has skills to do this. It's very simple. You pull on the rod under the wheel, and then you rotate the wheel to find the loose spot, and that's how you can decode almost all of the locks with this wheel combination, all the combination locks. Yeah, it's interesting. I mean, I think he has a tool for this. It's just a piece of metal with a notch. So one time, I think he opened the lock with a Red Bull can. It's a Red Bull can. He cut a piece off, and he cut a little snip, and he used that to open the lock. Interesting. All right, each wheel has 10 slots, yes, 0 to 9. The wheels can rotate freely and wrap around. Okay, the lock initially starts at 4 zeros. You are given a list of dead ends. Dead ends means if the lock displays any of these codes, the wheels of the lock will stop turning and you will be unable to open it. Oh, interesting. Given a target representing the value of the wheels that will unlock the lock. What do you mean? Representing the wheel to unlock. Oh, the code. Return the minimum total number of turns required to open the lock, or -1 if it is impossible. So the valid code is 0.0202, and we have these dead ends, so we cannot reach. So sequence of valid move is all zeros, and 1, 110, 120, and then there. Note that a sequence like 0, 0, 1, 0, 2, 0, 1, 0, 2 will be invalid because one of them is a dead end. The wheels of the lock become stuck after the display becomes 0, 1, 0, 2. Ah, I see. I see, it's interesting. So dead end is this. 0009. Oh yeah, I was like, you have to do 9 times, but no, because it's wrap around, so you can turn it both ways. So it's only one step. Very interesting. If dead end is this, yep. Oh wow, this is a very interesting question. Very interesting question. We have 500 dead ends. The target will not be in the list of dead ends for sure. The target on dead ends consists of digits only. Oh, this is a very interesting question. So we have some traps along the way, and we just want to know the shortest. It feels like a graph to me, right? So like these are the nodes. So if we can represent the nodes by these strings, there probably are better ways to represent, but we can talk about this later. So these are the nodes that does not have children, right? So these are the dead ends, and everything else have children. So we start from 0, 0, 0, 0. We start from here. There are so many ways to go, right? So we have 10 different ways. Yeah, so it's 10 So from 0, 0, 0, 0, we can go to 1. Oh, actually, no, I take it back. No, there's not, because we can only rotate the wheels for one step. So we can go to 0, 0, 0, 1, right? Or we rotate backwards, so we can go to 0, 0, 0, 9. Or we can rotate the second wheel 0, 0, 1, 0. Right, we can do that. And 0, 0, 9, 0. Or 0, 1, 0, 0. 0, 9, 0, 0. And the last one is 1, 0, 0, 0, and 9, 0, 0, 0. That means for each one we have 2 options, and we have 4, so I have 16. No, not 16, we have 8. We have 8. 8 different children from 0, 0, 0, 0, right? And we just do a BFS, a breadth first search, to see when we can reach the target. And if we hit one of the dead ends, then we say it's a bad, and we cache along the way as well. Yeah, we cache it along the way, so we know from, like, say from a certain combination, and no matter where we go, it's going to end in dead end, and then that one is a dead end. Okay, so is there a better way to represent the state? I mean, we can definitely use string, but I feel like there gotta be something better. I mean, we can represent this as numbers, right? If we represent these as numbers, how do we do, like, going 1? So like at 0, 2, 0, 1, right? If we want to change this can be 3 or this can be 1. We can go front or go back. I think that's an interesting question. The simplest way is a list, right? The simplest way is a list, and we can modify any value in the list, +1, -1. It's actually +1, and how do we wrap around? Like mod or -1, the 0 -1 is -1, so we just stipulate that 0 -1 equals 9. But if we do this as a list, then it cannot be used as a key. Can we do like a bitmap? I don't know. I mean, we have all the digits, right? So we have all the digits, or 10 digits, but we have repeats. That's the issue. We have repeats. We have repeats. Can we handle the repeats? I don't think we can handle the repeats. Repeats can be like if it's a set, right? If it's a set, then it'll be easier to handle. But this is not a set. Zero exists, 1 exists. Yeah, we can only, if you use bitmap, right, we can only say which number exists and in what order. That we can do. But this one is slightly different. But the thing is, but there are just numbers, right? They're just numbers. So if we can handle the number like +1, right? +1, +10, +100, +1000, right? That's moving like up. And then going back down would be -1, minus 10, minus 100, and minus 1000, right? And if and the only situation that is when we have a 0. Right? That's the only case that if we have a 0 and we minus, say this one, minus 100, minus 1000, and then that's going to be a 0 minus 1, and that's going to be problematic. So when that happens, yeah, I just want to see if it's possible. So minus 10. Is there like a better way to check? A better way to check the digit at any position? I mean, we can do, we know the digit, right? We just do divide by 10, divide by 100, and then we mod by 10. Then we know the digit. Yeah, we can know the digit, but there could be an easier way to say if minus 10, right? I mean, the idea is the value minus 10 minus 10 or minus 1000. So if we want to do 2 digits, right? If we want to do 2 digits, and then we do mod 100, then we get this value, and we compare this value to 10. If this value is larger than 10, then we say it's good. We can do minus 10. If this value is smaller than 10, then instead of do minus 10, we do plus 90. Yeah, that's how we can go. Okay, I think this is a way to represent the state. And the rest is just to do a DFS with, yeah, DFS when we find it, and that's the first one, yeah? And then we put it in every time we go. All right, let's try it. I think it shall work. So fourth, okie dokie. Let's take a look. V and this, delete the previous one. There's a hint. Let's see if this one works, right? Okay, so dead end. How large is a dead end? The dead end is 500. That's too much. So we're gonna turn everything into a number. Everything gonna be turned into a number. So we're gonna say end nodes equals set int d, right? Int d for d in dead ends. All right. So we have end nodes. Now we have a start node, and then target t node, right? Target node is going to be int target, right? And then steps is going to be start from 0, and visited is going to be another set, right? No, it's actually not. It's going to be a dictionary. It's going to be a dictionary, and everything shall be. Nah, that's fine. It's going to be a dictionary. Right? Visited is going to be a dictionary, and then the current node is going to be 0. We start from 0, right? And actually, we shall say zero and none. Oh, we can use value. Let's just say -1. -1 means we haven't got it yet. but we are visiting it right now, right? And what's next? Well, actually, this is going to be a queue. Yeah, we're going to do a queue. Q going to equal to 0, right? And then we say while Q, right? Temp equals another 1, and we say for hold on. For node in Q, right? So we get the node out, and then we for node in Q means we are we already put in. So we just say for node in Q, right? We need to find the children of the node. So we have multiple child. So for children equals to, so the node we can plus plus 1000. Yeah, we can say, like, if it's 9, right? If 9 something or plus 1000, that'd be 10,000, and we mod 10,000. Yeah, we mod 10,000. So children gonna be node plus 1. Oh, what if it's 9 plus 1? Then it will. Ay. This is okay. Okay, this is not as straightforward, right? Not as straightforward. So we want a plus 1. It depends on the current value. So we're gonna have to check, like, children, right? Children gonna be this. Let's say if node 10, that's the last digit. If the last digit is equal to, if the last digit equal to 0, right? Then children dot append node plus 1. That's for sure. No, a dot extend. We don't have to do this. We just let's just go, right? Let's just go. If node equals 10, so child 1 equals node plus 1. Actually, let's just say if node plus 1 not in T node. Hold up. How do we, if node plus 1 is the children not in, what if it's in T node? So I think what we can do is visited. Yeah, so we're gonna say this is going to be a dictionary. Let's put this as a dictionary, right? And then this is going to be 0. So these are dead ends. So this is going to be visited. Visited is going to be this. And visited, target, step. Okay. This is visited, and we say if 0 in visited, return false. Oh, return 0, right? Return -1. Return -1. There's a dead end. Else we say visited 0 equals to -1. This is an unknown. And then we set this, we set this, we set the Q, and then we start going. So this is the next node. So we say if and this is for the current node, right? This is the current node. We want to know all of its possibilities. I feel like isn't like you're doing the yeah, we don't have to, we just need to keep track on the steps, right? That's all we need to keep track on. So steps 0, 1, 2, 3, 4, 5, 6, right? That's 6. So it is start from 0, and at the end, when we go through everything, at the end, we're going to say steps plus equal 1, right? So we'll go to the next one, and then Q equals to 10, right? So we'll go to the next one. So here is if this one is not in visited, if this one is not in visited, we don't need this. It's just a set, right? We just need a set. If it's not in visited, if it's not in visited, then we can visit it, right? We can visit it. Yeah. If it's not in visited, then we say temp.append node plus 1, right? Then if node, because that's a 0, so we need the plus 9, plus 9 not in visited, we say temp.append node plus 9, right? So this is 2 ways for the last digit. Now, if node do 10 is equal to 9, right? Then we say if node minus 1, right? We'll go forward, which base is minus 9 because we go to 0, not in visited. Then temp.append node minus 9. Same thing, if node minus 1, not in visited, then temp.append node minus 1, right? But every time when we do this, if it's not in visited, so visited.add node plus 1, right? We have to add it for each one of them. So this has to add, and this has to minus 9, going forward, and this one is to minus 1. So we will do the, so if equals 0, and then we say elif, it's equal to this, and the last piece is else. So it's not 0 nor 9, so we can do plus 1 and minus 1. So basically we just copy and paste this code, right? And then this we need to say we can plus 1, right? We can do plus 1 for both, and we can do minus 1. Yeah, and it's, I just need to put this in the visited, that's it. So yes, I just put in a set to say this one is visited, so we just don't go anymore. So visited, and if the 0 is in it, and we do this. Otherwise, to minus 1, right? And then Q is 0, and visited dot add 0 as well, because 0 we have visited. And then we go to the Q, and then for node in the Q, which is 0, come out, and we go all the directions that 0 needs to go, right? All the directions 0 needs to go. If I can go, I put it in, oh, it looks like I visited, yeah, visited added, so temp also added, visited added, temp also added, right? That's for the next node. Let's see if I can go. I can go, right? And then for the next one, if it's in, then we don't do it. Okay, so this is just for 10. We have to check for 100 and also check. So this is going to be a function, right? It's going to be a function. So we say def, def what? For node in queue, find children, right? Find children. So we need what? We need digits. We can call it the tens, right? Tens, and we need to pass in visited, and we need to pass in the temp, right? I shouldn't call it temp, just like the next level. Let's call it next level. And this one going to be a none, nothing is returned. So tens is going to be an int. Visited is a set of int, which I think I have to do here, a set. And this one is going to be a list of int, right? I think I forgot the bracket here. Okay, so when I say, it's not 10, it's gonna be digits, dig, let's call it dig, right? So number of digits from the right side of the count. So we say, oh, and also the node, and then passing the node as well. So the node is gonna be an int, right? So we say if node, so the tens is gonna be 10, do this digit, right? I'm gonna be like from digit 1, 2, 3, or 4. And then I'm gonna say if node mod tens equal to equal to what? 10. No, equal to not equal to. It's gonna be smaller than smaller than what? Smaller than 10 digit minus 1. Alright? So the smaller than digit minus 1, like if it's gonna be 100, right? It's gonna be 100, then we get 2-digit values, and we need to see the 2-digit value is smaller than 10. That means we're starting at the 0. So this is a zero situation. Then we say if node plus 10 digits, so is that tens? That is going to be digit minus 1, right? That's going to be digit minus 1. So has to be digit minus 1. So we have tens. This is going to be the mod. Yeah, that's going to be the mod. And this is going to be the change. Let's call this one mod. This one we're going to mod with. And then change is going to be mod divided by 10. Right? So we say node mod if it's smaller than change, like the minimum change. Then we can say plus change, right? If this plus change not in visited, then visited dot append dot add node plus change, and temp dot append node plus change, right? And then if node So we know it's a 0, right? If it's a 0, then we need to plus 9 times change, right? Or 9 times change. If this one not visited, then we say the same thing. Plus 9 times change. This one gonna be 9 times change. So elif node the mod, not mode. Right. So if we're here is, so we're talking about the 9 situation. The 9 situation means what does it mean? It means if I mod like 4 and then be like 999 something, right? So that means if this thing is equal, no, this thing is larger or equal to, if it's larger or equal to mod minus change, right? Mod minus change. Mod, starting mod is 10, change is 1, so larger equal to 9, which is true. If the mod say that's 1000, right, then the change is 100. So 1000 minus 100 is 900. And if it's larger than the starting is a 9, okay? The starting is a 9. So we say if node plus, oh, it's starting with a 9. If it start with a 9, then we need to minus 9 times change, right? Minus 9 times change, not in visited, and we say visited dot add node minus 9 times change, and temp dot append, also node minus 9 times change. If node minus change, right? Going that this one is going forward and this one going backwards. Minus change, not visited. Then visited.add node minus change and temp.append node minus change. Right. So this is second situation. Last situation, it means I can do anything. I can just plus change, not in, visited. I think I can combine these situations together. Let's do that later. Let's get it one going first. Like currently the logic is working for me. I don't want to make any change to it. Right, so this is the logic, and after that, then we're done. Right, after that we're done. So find children, which means this entire code it can be simplified by for node in queue, then for digit in range from 1 to 4, right? 1 to 5, so if 1, 2, 3, 4. We say find children. Oh, we should also have a flag, right? We should also have a flag of whether we find it. That's fine. We can check on the visited because we push everything into the visited. So say find children, current node, digit, visited, temp is next level. Yep. So we go through all this, right? For the current node, we go through all possible combinations for the next one, and we're gonna check. We say if, right? If target t node right? If t node in visited, we don't have the visited yet, then we can return immediately steps plus 1, right? If we find it inside, then we immediately return. If not, we go through everything, and then we do this, then we do this. Until we, when is the end? Well, the end is the queue, right? Which means if I end up here, that means the t node has never been visited, right? Then we simply say return -1. Okay. No, it's actually if, hold on. These are the dead ends. I don't think I use the dead ends well. Well, the dead ends just means I don't go from there, right? I don't go from there. So if I initially, yeah, so if 0 is even visited, then there's no way I can go. Which means I should put 0. If 0 is inside the dead end. That depends. I cannot return -1. It depends on when I return -1 if t node is when I return hold up. I need to check the 0 as well. So you're saying we don't check it in the children side. We check it every time we see it. Now my point is if the children doesn't go, if I cannot go to the children, I just don't go to the children. Yeah, so therefore we have to check it first if the 0 is in the visited. We call the dead ends as the visited, right? And if 0 is in the visited, then if t node is 0 itself, then we return 1. No, that's going to be 0, right? Yeah, that's going to be 0. Else, then that's going to be -1 because we cannot reach it. And then we say we'll put 0 in it, right? A visited also put 0 in it, and then we come out. And node in, but still we did not consider the situation because we didn't check on the 0. We can have something that can go to 0. Anyway, so if 0 is invisited, we do this, and then we say if t node is equal to 0, then return 0. Which we can make this even simpler. We check the t node first, right? And we check this, and then we starting from 0, we go to temp, we put the node that we can go, and then keep going, and time the test. Alright, so the test case, first test case is this. I'm going to remove the clutter. Actually, I can remove the clutter at the end. Second test case is this. So we're going to put 6 here. Maybe a tuple. Second test case is 1. Third test case is going to be -1. This one's going to be -1. The last test case is going to be a -1 as well. This one's going to be -1. And I think this one is going to be a 0. That's what I think. Okay, now let's remove all the clutter. these has to be this. All right, and all of these need to disappear, and all of this here again. Okay, so change this into dead end and target, and this one is open lock, dead ends, target. Try it. We have error, undefined name, find children. But of course, undefined name, temp, that is temp. We don't have self. And here we have to call it self. Okay, try again. Oh, we passed all of them. That's good. Try here, but we're gonna custom test case. Do 0, 0, 0, right? But this is also 0, 0, 0. This shall give us. I think this is a 0. I'm not sure if this one. Find target in dead. Oh, target is not in dead ends. Oh, so target is not in dead ends. Did I change our stuff? No, actually it's fine. It's just this is gonna be 0. Yeah, target is not in dead end. If target is not in dead ends, but 0 is in dead end, then yes, I think this one works. All right, try it. Did I click it? There we go. Pending, judging, accepted. Good. So it is a graph. So we treat each possible combination as a node in a graph. From each node, there are 8 possibilities. 8 children. Yeah, there are 8 children. Yeah, there are 8 children obtained by turning the wheel on each digit either forward or backward. We start from 0, 0, 0, 0. We start from 0, 0, perform a DFS, and return the depth when the target is found. The tricky part is to find all 8 children. We can use find 8 children. How should I put it? In order to represent the node as something hashable, hashable and easy to manipulate, we turn each node into an integer, right? Into an integer representation of the original str version of the combination of the code, right? I'm gonna call it the original str version. Let's just say the original str version. We turn each node into an integer representation of the original str version. Then we compare. Then we check the digit at each position, right? If it is a 0 or 9, it has to be treated separately. And from there we can obtain the 8. 2, 3, 4, 5, 6. Why is the count like only 6? Like each position. Oh no, yeah, that's right. Has to be treated separately because from 0 going backwards, we end up with 9, and from 9 going forward, we end up with 0. Actually, it's just a 0. I just realized we don't have to do this. We don't have to do this. We can just plus CHG, right? So this one plus CHG, and we can mod. We can mod. Oh no, we cannot. Unless we grab the value out. If we grab, so here we didn't grab it out, right? We just, for each digit, right? If we grab the value out, then this should be the only thing we compare. Yeah, maybe it'll be easier. Hold on, let me, yeah, let this, if it is 0, it has to be treated separately because 0 going backwards. 0, because from 0 going backwards, we end up with 9. And that's it. But I want to make a little bit change to here. So we have, let's call it, so the mod is this, the change is this, and the target to be changed. To change is equal to node, the mod, right? And we also have remains, right? And what should we call it? This one will be the node minus this. So to change is this. The rest is node minus to change, right? So now what we can do is if to change is smaller than change, right? If basically we just say if this, then we say if rest plus to change plus this, and then we're gonna do this, right? We're gonna do this, we're gonna do this, and this one's the same. So instead of node, oh, actually, no, wait, we can still do this. Node, right? It's fine. It's here. I think we can just do else, right? Else. We can just do else, and we just say if node plus node plus change, but it's not node plus change. It's rest. It's rest plus to change plus change, right? And this one we have to mod a mod, right? If this is not invisited, right? Which means we have candidate 1 is going to be this value. So we're gonna just say candidate is going to be this value, this value. You can complete. So we're going to yank it, I'm going to delete it. And paste this. And just to be more explicit, this has to be this, right? We say if candidate 1 not in this, then visitor.add candidate 1, this one also add candidate 1. Otherwise, if node minus change, so we can always do minus change. In other words, right? In other words, this is the same as this. It's just this thing. So what we can do is, if this is smaller than this, then we need to do plus 9, which means we can do this one. Everybody will do this one. Right? Everybody will do this one. So we say this one is wheel going forward, right? Wheel going forward. And then next one is wheel going backward. And this one we have to make this. Say if this is smaller than this, and if this, then we do this, and else, which means it's larger than we can do minus. Yes, okay. So let's also make to change this, rest is this. So we can rest only use it once. So let's don't put another one. Let's just paste this one here. No rest, so we have to change. So that's going to be minus this plus this if candidate 1 is not a visitor, we put it in, right? And going backwards depends on whether we're gonna plus 9. Maybe we don't. Maybe we can. Yes, we can do candidate. We can do candidate 2, right? Candidate 2 equals what? It's going to be to change plus 1,000, right? To change plus 1,000. So it's to change. So it's node minus to change plus to change plus mod minus change. And this one we're gonna mod, right? And we can do, so we have candidate 1 and candidate 2, right? So these two we can do it this way. If candidate 1 is not visited, then we do it. And also if candidate 2 is not, then we can do. So change mod, so we make it much easier now. Let's see if it works still. Yeah, it still works. So it's the easier version. Yep. Okay, let's first see what's the runtime of this thing. And then we're gonna do another solution, right? Another solution, and submit, pending, judging, accepted. So I have 2. Let's kind of see. This one we hit 624. Oh, wow, this is faster. So let's record this one, this version. So this version is, what's the runtime? What's the runtime? Well, runtime is we have to visit every single one of these. I mean, technically speaking, the runtime is 01 because we only have how many nodes? 9,999 nodes to visit, right? Yeah, we only have 999 nodes to visit. So technically, right? Technically, complexity is 01 because we visit each node only once, and there are only 9999 nodes. The runtime for this, we picked a good one, is 372, which gives us 95% ranking. Well, did pretty well on this one. 95% ranking. Yeah, once we simplify, this just needs a little bit of simplification on how we can do this. All right, minus this plus mod minus, yeah, this is the tricky part, right? We want to go to 9, want from 0 to go to 9. Instead of plus 9, we add a 10, right? We add the mod, and then we minus the change, and then we'll go back to 9. There we go. This is pretty straightforward. I don't think anything else needs to be mentioned here. We have steps, we have the queue, we have the visited, and it's just a common play for the queue. And then we find it, we immediately return. Yep, I think I'm satisfied. Right, let's take a look. No solution for this one. This is definitely a medium question. Problems. I think it's a medium question. Open the lock. Yep, it's a medium question. It's like a medium. That's how I think this one is. A medium question. Good one. I like it. Yeah, I don't think that's a good interview question though. Regular Java BFS and 2N BFS with improvement. How to avoid TLE? Why would you TLE? Shortest path. BFS is the best way to go. By using deck and pop left. Using list and pop 0. Why would you pop 0? I mean, yes, you can use deck, but you can also use this. Open lock, successors. Oh, they're using what is this? Number and source this and num minus 1. Oh, they take the str version, right? They take the str version and they do this. What if it's a 0 minus 1? It's minus. Are you telling me minus 1 mod 10 give you 9? I doubt it. Minus 1 mod 10. Ah, how do you know? Minus 1 mod 10 is 9. Oh, wow. Okay. Okay. That's fine. Yeah. Set the ends. Deck is this. Queue. Size, you manage this every time pop up. If you notice target, return depth. If you node in visited, continue. Otherwise, we add this and queue.extend. Self-successors node. Node, we go through each one, we add these two. Oh, similar, not similar, I think it's the same solution. Yeah, we didn't realize this. Yep, I didn't know. Did not know that. Oh, I probably need to upvote this one as well. Yeah, let's upvote this one. 16 lines. BFS. Everybody's a BFS, so that's it. That's it. I mean, there's not much to say. It's always BFS, and I have my way of writing BFS. Yeah, I have my and it's different. Like in my case, I add the children into the visited. In their case, is they visit each node, and then they check if the node is the children. So that's why I have to check at the end and return steps plus one. But they do it differently. I like my way. I like my way. Okay, that's it. That's it for today. Did pretty well. I'll see you guys tomorrow. Adios.